This will be the last matrix for the concept on or topic on kernel and nullity of a linear transformation involving a matrix here. This is a 4 by 4 matrix. So m by n is 4 by 4. So this linear transformation is just easy. You have r to the n to m to the m. So you have here r to the 4 to r to the 4. Even if this is very easy for this matrix, why do we always start with this? The reason for that is, of course, the goal here is to solve, because we are talking about the kernel. The kernel is a set of all v. With this linear transformation, a times that set v equal to the zero vector. Okay? But what zero vector? This is not the purpose. This would be the set containing a zero vector, and since it's R4, our zero vector is a zero vector in R4. Not in R3, not in R2, but more specifically in R4. That's the purpose of this. Aside from that, this here is where our v will come in. And since we're solving for all vectors v, our vector v here can be represented in R4. V sub 1, v sub 2, v sub 3, and v sub 4. Okay? Again, even if it's too easy here because we have a square matrix, for some cases, we cannot automatically declare that the zero vector is R3 or R5 or R2 because we need to really start with this. So anyway, we already have that. Let's start now with this. Before we use this method, let us come up here with the reduced row echelon form of this matrix, so that once we are going to multiply this with vector v with these components and equating to the zero vector, it's easier for us to solve for the components of v sub 1, v sub 2, v sub 3, and v sub 4. So let's copy it here, and I have a lot of space at the bottom. Please bear with me. This may take a lot of time, but of course, this is the reason why we have this video as part of your review. Since we already have a leading one, our goal here is to make these other entries be equal to 0. So what we can do here is this. Multiply negative 3 to row 1 plus row 2. So this will be 0. Next, multiply 4 to row 1 plus row 3 rather to have a new row 3 to make this 0. And simply add row 1 and row 4 to have a new row 4 since this will become 0 when added. So we'll have this form here. We have still 1, 2, right? Negative 1 and then 4. Negative 3 times 1 is negative 3 times plus 3, that's 0. So negative 3 times 2 is negative 6 plus 1, negative 5. Negative 3 times negative 1 is positive 3 plus 2, I have here 5. Next, negative 3 times 4 is negative 12 plus 1, so you have negative 13. Next, 4 times 1 is 4 plus this, 0. 4 times 2 is 8 plus this, you have positive 5. 4 times negative 1 is negative 4 plus this, negative 5. 4 times 4 is 16 plus this, you will have 13. Okay? R1. Add this to 0. Add this, 0. When you add these two, 0. 4 plus 1, you will have here 5. 4 plus 1, that's 5. Okay. So, however, look at this, what happened here. Okay? Look at what happened. You have two rows which are actually multiples of the other. Simply multiply negative 1 to row 2, you will get row 3 or vice versa. What does this mean? In the previous understanding, if we have rows which are multiple of the other, one of which is a row of 0 when continued, and we'll have this. Okay, let's try. Let's try to make this first leading one. So negative 1/5 of row 2 for on your row 2. 1, 2, negative 1, 4, 0. This is positive 1. This is negative 1. This is positive 13 fifths. 0, 5, negative 5, and positive 13. 0, 0, 0, 5 here still. It is what I meant earlier. If we're going to multiply negative 5, take note that we just multiplied negative 1/5 and now we're going to multiply negative 5. But of course, the goal is to make this leading 1 and now to make this 0. So negative 5 row 2 plus row 3 to have a new row 3. 1, 2, negative 1, 4, 0, 1, negative 1, 13 fifths. This is 0. Negative 5 times 1 is negative 5 plus 5, 0. Negative 5 times negative 1 is positive 5 plus negative 5, 0. Negative 5 times 13 fifths, sorry for that, is negative 13 plus positive 13, 0. This is still 0, 0, 0, 5 here. Since we have a row of 0, let's interchange row 3 and row 4 because the row of 0 must be on the bottommost part. 1, 2, negative 1, 4. 0, 1, negative 1, 13 fifths. 0, 0, 0, 5. Then 0, 0, 0, and 0. Okay. Last step is to make this here 0. I mean 1. So that it will be leading 1. So we'll have here 1/5 of row 3 for a new row 3. Okay. So 1, 0, 0, 0. 2, 1, 0, 0. Negative 1, negative 1, 0, 0. We have 4, 13 fifths. This will be 1, and that's 0 now. Okay. This is still the row echelon form, and our goal is the reduced row echelon form. Hence, other entries aside from leading 1, this one here, this, and that should be zeros because the same column contains leading 1. Okay, we don't need to make this two zeros here. It's okay as that because it doesn't have leading 1 there. So let's start with this 2. So negative 13 fifths of row 3 plus row 2. So that this would be 0. Then negative 4 of row 3 plus row 1 for new 1, so that it will be 0. Okay. Whatever be the result here, I'm going to write it in the other part here so that we will have a lot of space here. 1, 2, sorry. Yeah, so since we don't have other forms here, so you have 0, 0, 0, 1. So this is negative 1, this is negative 1. So negative 13 times this plus that, 0. Negative 4 times this plus that, 0 as well. Okay. Next is to make this 0. Okay. We will simply multiply negative 1 to row 2 plus row 1 for a new row 1. Okay. Again, this is what I meant. I'm going to place here. But let me rewrite it again. You have 1, 2, negative 1. Sorry. 1, 2, negative 1, 0. 0, 1, negative 1, 0. 0, 0, 0, 1. 0, 0, 0, 0. Let me check. 1, 2, negative 1, 0. 0, 1, negative 1, 0. And then 0, 0. That's correct. Again, we're going to multiply negative 2 to row 2 plus row 1 for a new row 1. We have here 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, negative 1, 0. This is still 1. Negative 2 times 1 is negative 2 plus this, 0. Negative 2 times negative 1 is positive 2 plus that, positive 1, and this is still 0. This is now the final form of our reduced row echelon form. Okay? This time, we're going to use this process now and multiply this with vector in R4 and equate it to the 0 vector in the same space, R4. Okay. Once you multiply that, it's easier for us to solve for the components of v sub 1, v sub 2, v sub 3, and v sub 4. So our first equation is v sub 1 plus v sub 3 is equal to 0. Next, v sub 2 minus v sub 3 is equal to 0. And then we have here the v sub 4 is equal to 0 as well. Okay? So this is exact. V sub 4 is 0. However, for v sub 3, we can assign v sub 3 be t. This would mean v sub 1 plus v sub 3 will become v sub 1 plus t equals 0. So v sub 1 is equal to negative t. And then our v sub 2 minus v sub 3 equal to 0. V sub 2 minus t equal to 0. V sub 2 is positive t. Okay. With this, our vector in R4 is negative t, positive t, and then 0. Okay? Because that's the only exact result. In short, our kernel of t is a matrix containing that. As we factor out t here, we have 1, sorry, negative 1, 1, 1, 0, such that T is an element of R. This is our kernel of T. And the nullity of T is the dimension of the basis of your kernel. Okay, the basis will only contain this, so the nullity here is equal to 1. Okay, the nullity is 1. This is our kernel. The basis is actually just this here, a set containing this vector here. So this is how we solve for the kernel and the nullity of T of this given matrix, which is a 4 by 4 matrix. Thank you very much for watching.